people who refuse to be here. There we go. Is it going? I think it's going. All right, so let me write this down. So this is number 1, which we did go over, I guess, but we went over it too quickly. So number 1, we have this function, f of x. And if we can do this one, we can do almost any of them, I think, except for maybe number 7. Someone was complaining about that one. And we have, what are we doing here? X, O. Okay. There. Okay, so there's the function. We're just supposed to come up with the expression, the Newton's method expression. The Newton's method expression just says that x in plus 1 is equal to x in minus f of x in over f prime of x in. Did I get that right? I hope so. It is. All right, so there's Newton's method. It comes directly from the linear approximation of the function. So we're just supposed to plug this in. So let's get, we need f prime of x, easy enough, 18x. And then just shove these into here. So this is going to be x of n minus f, which is 9, x in squared minus 2 over 18x of n. So I think they wanted you to write something like this. I think the confusing thing is the whole subscript notation business. Let me see if I can type it correctly. It's not too bad, I don't think. X subscript in. And by the way, to get the subscript without touching my mouse, and I hate the mouse with my whole heart, what I do is I type X and then underscore, and it drops it down. So whoops, I guess I have too many parentheses there. You can never have too many parentheses. And then I use the shift 6 to get the exponent. And I just have to make sure everything looks good. And then the slash to get the bottom here, 18x. Whoops, not that. Subscript in. I think that is it. Let's find out. Is it going to let me submit in the teacher mode? What?
What is the f of x equals 0?
Oh, okay, we'll get there in a sec. Why is it giving me a hard time, though? Oh, it's because that's a 2 there and not a 1. How did I change it to a 1? There we go. Make it a 2. Let me see if this is right. Still not right? Anger management. Oh, you know what? The parentheses down here is probably a problem. Normally, I would say that you can't have too many parentheses.
Yeah, I think that's it, because we have the same number.
There we go, okay. Okay, so this thing is just saying that what you're trying to do is you're trying to find a root. In Newton's method, so let's go back here. So here's Newton's method. Newton's method says you have some function. It's like thumping and bumping.
Oh yeah, they were doing that before anybody else got here too.
Well, anyway, you've got this function, f of x equals 0. We're trying to solve this. So in the, like if you had something like this, x squared plus e to the x equals 0, that would be a nightmare because I don't know how to solve that. I mean, well, no, that's actually not enough of a nightmare. Let's do this plus natural log of x. There. Now, I don't know how to solve that, but Newton's method to the rescue, what you do is to solve an equation like this, or like this, you take this part, you name it f of x, and then you plug it into this sort of form, x in, f prime of x in, and that gives you this iterative way of getting closer and closer to the truth. And so each of these steps, so that f of x 0, that's just saying f of x equals 0. It's just saying we want to solve this equals 0 using Newton's method. So it's kind of superfluous for what we're doing here. You're not actually solving anything. You're just saying, here's the form I'm going to use, and you're going to do this over and over again. You're going to write a recursive function on your computer there. And so the next one is going to be this, and then you plug whatever answer you get into this again and over again. You know recursive functions, I'm sure. And so that's all Newton's method is. It's just a recursive function to get the root. And that's how your calculators actually get the roots. That's what you're, so when Ethan is bragging about his calculator getting roots for him, it's just doing Newton's method. There's that. Okay, actually, I should qualify that. There are other methods for finding roots. Newton's method is the first one. And your calculator probably uses a slightly different method, to be honest. It probably uses either the secant method or the false position method, but they're all similar. It's a similar sort of iterative process. The formula is just slightly more complicated. Newton's method is kind of like the easiest version. And it does a great job, Newton's method, generally. Okay, so that takes care of number 1. And some people were complaining about number 7, did you say?
I'm good on that.
Oh, then we don't need to do number 7? Okay, which other one do we need to do?
I need help with number 5.
Okay, 6, 5. Here's my number 5. Does it look sort of like your number 5?
It's the exact same.
Oh, amazing. So, joyous tidings. We get to do exactly the same for you. So let's do it. So we have this function. So let me write it down, and then we will do it. X cubed plus x plus 3, and then x1 is -1, and we're supposed to come up with x2 and x3. So essentially, they just want you to plug this into the iterative function. So Sienna, what is the derivative of this function?
3x plus 1.
You guys are getting great at this. Oh, did you say 3x squared plus 1?
Oh, yeah.
Okay,
Sorry.
I knew you were thinking it, and so I
Yeah.
wrote it down as such. And then I just realized, oh, that's not quite what I heard, is it? Okay, so there it is. There's that. And then I could write this, that x sub n plus 1. So the next iteration, or the next approximation, old approximation, minus x cubed plus x plus 3 over 3x squared plus 1. So essentially, to get x2, I'm just going to plug x1 into this. And it just slid down for some reason. So x1 is -1. I put -1 into that, and I get this, -1 minus -1 cubed plus -1 plus 3. Give me a sec here. Okay, so this is going to be -1. Okay, it's -1 cubed is -1, -1. Okay, so this will be 1 over 4. So 3/4, 0.75. And then to get x3, I'm going to do the same thing. That'll be, except for I'm going to use 3/4. So it'll be 0.75, 0.75 cubed plus 0.75 plus 3 over 3 times 0.75 squared, and get whatever my calculator gives me, which I don't know what that is going. Oh, I blew it, didn't I? I messed up here. Sorry, let me highlight. Yeah, don't write it all down yet. Sorry, I messed it up right here. That is correct. The next one, that's wrong. That's all wrong. So here, I'll get rid of the wrong stuff. Sorry about that. That should be -5/4. I thought it was a little weird that it turned positive all of a sudden. So that's -1.25. That means all of these get changed, sadly. Let's see if I can change them in mass. No, I can't. Well, sort of. So it'll be -1.25, 1.25, 1.25. Yeah. Anyway, hopefully that'll give you what. I'm curious, though, to see, because we had the issue with who was it? Was it Allie? You had an issue with hers on this these approximations. I just want to see if this approximation, -1.25, see if it likes me. Oh, it liked me, I guess. And then the third approximation, if you pump it into your calculator, what you're going to get is hopefully this. So type quickly before I. But the important thing, though, is that you understand where this is all coming from.
Yeah.
And you can get it. You can get it with the function. Are there other issues with this homework that we need to do? We love this homework. But maybe you don't love it. But I don't know. I find it kind of cool that you can use calculus to solve algebra problems that are too hard to solve using regular algebra. Right, you wanna give it a go? Yeah, you do. Let's see, no, this is not what you want. This is wrong. Let me find something that you do want. Hold on a sec. This one's good. Alright, hopefully this isn't too painful. So we'll give it a try. Here you are, enjoy. What's that? Yeah, it's gonna be fun. I'll put the formula up on the screen for now. Well, I'll get it up there just so that you all can enjoy it. Oh, I do not. I took them to my office and they all disappeared. Do you not have one? Do you have like a phone or something you can use? For quizzes, I'm a little bit more liberal with it, but yeah, I'll bring them for when we have our exam. Sorry about that. Wow, you have extra calculators?
No, I lost one in the calendar and I already bought it.
Okay, nice. All right. Well, anyway, I'll put the formula up here in just a sec. So if you can't, you probably can remember it, but just in case, since it was on your homework, it's like they thought you couldn't remember it for the homework. Set up. Uh-oh. What just happened? Okay. Almost there. Please. Just jot this down.
Doing the question in math then.
Oh, great. I'll fix it. Why did it do it for me? That's nice. Okay. I don't want to rush anyone. I guess if you're slow typing on your calculator, it'll take you a little longer. Tomorrow. We aren't here. We have more pictures. Everyone's done with the quiz. Yeah, might as well give you all the pictures. I printed up the one set of pictures, and then I was like, oh, I like those better. And it's like, oh, well, I said, you just print up the other set of pictures. And then we got lots of pictures. So many pictures. This will save you having to try to copy all this down. Okay, let us do this. Quiz time. Where am I? Okay, so hopefully you all got started out correctly. There it is. And you figured out the derivative, and you wrote your little Newton's method iterative little thing there. And then I don't have a calculator with me, so I ended up just using my computer. So I took that function. Hopefully I typed it in correctly. We're going to find out in just a sec. Let's see. Let's just type it. Did I do that right? Let's see, can I move this over? Apparently not. There. Now I can sort of see it here. So it's x minus 3 cosine x plus x over 1 minus same thing as that. Okay, yeah, I got it right. Okay, so then I was like, hey, look, I can just evaluate as a floating point. That's what I'll do. This function at 3. So here I saw a lot of 2.947s, and then I did it again, and then I thought, you know what? I could just do this over and over again since I've already typed it in. It's not too difficult to just say, let's crank this out. And so I set this up. There's the beginning. This is what, the power of Newton's method and other methods like this is you can just get it started and then have a computer do this for you. You could do this in Microsoft Excel. I just have this old, literally 30-year-old program that I have on my computer. So anyway, there's the starting point, and then I'm like, okay, let's do this 100 times because I'm curious to see how close it gets. And so I basically had to do it. There's the first one, second one you recognize, but then the third one you didn't recognize, but then check it out. After the fourth, wait, is it the fourth one? Yeah. After the fourth one, it doesn't change at all, which means that after 4 iterations, we're within 10 digits. Like you've got 10 digits that are correct. So it only took 4 iterations. This is why your calculators can do this so quickly, give you an approximate root. It's an approximate root, but it's good to 10 digits. And all it needs is 4 iterations. There's a course that we have here called Numerical Methods where we actually talk about like how close you're going to get, how fast you're going to get it there, and so forth. But I was actually somewhat surprised that it went so quickly for this one. Usually it takes maybe 10 to settle down, 10 iterations. I must have just picked well. Okay, so we're moving on though to new stuff. I've given you a bunch of stuff there. Let's see, can I make this not be dumb? Probably not. But anyway, should I take a picture? I've got the file on my computer. So our goal, I'll just go to the PowerPoint. That's always safest, right? goal is to come up with areas. So we're switching from the idea of slopes to the idea of coming up with areas. Areas, and you already know how to compute areas. You've had geometry, haven't you? Most of you have had some sort of geometry. It's required, isn't it? Anyway, so you could come up with this area. I'll bet you can come up with this area. I give you a diagram here, a nice rectangle. You've got the coordinates of two of the corners of the rectangle. I'll just tell you now that that is a rectangle. You come up with the area. I'll find someone at random to tell me the answer. And if you're watching the video, you can do this yourselves, I'm sure. Let's follow along. Whoops. Excuse me. There we go. That's not what we want to do. It's been a week since I've been using this app. There it is. All right, randomize. Oh, you're not here, but you could do it, I'm sure. But Elena, do you know the area of this rectangle?
I have no idea, I was estimating it, 42 square units.
Yeah, 42 square units. Very nice. Because it's 6, wait a minute, 6 across, 7 up, right? Is that the way it works? Yeah, beautiful. Okay, let's make it a little bit harder. Oh, how in the world? That's
Just a messed up.
That's messed up. Why is that like that? I don't know why that's like that. Let me just fix it. That's dumb. Okay, 3, 3. There we go. Okay, how about that? Now I've got this weird figure. It looks like it is the union of two rectangles. So see if you can come up with this particular area. I'll bet you can. I'll give you a minute. Or, yeah, the area that's blue here. All right, Allie, do you know what the area is for this thing?
30.
It is 30, yeah. So you basically just added the two areas together. Very nice. So we can add those two areas together. Now, why do I have this? Oh, I know why I have this. So here's another area, a slightly different area problem. But here I give you the function, and I want to know the area between that function and the x-axis. Still a rectangle, though, just as a hint. I'll bet you can do this in your head. You've probably already done it. I'll give you just a minute, nonetheless. Well, Sienna, do you know what the area is of this thing? I know it's early. Length times width. So what's the width of the rectangle?
6.
It is 6. And how tall is the rectangle?
23.
It is 6 as well. Very good. So this is 6 here. This is 6. So what's the area? 36. Very nice. 36. So yeah. So this is all well and good, and it's all well and good until you throw something like this into the mix. And now suddenly, what do we do? Y equals 9 minus x squared. How do we find the area of this thing? So this is something that has puzzled mathematicians actually for millennia. And Archimedes actually solved this problem. He had a formula for the exact area underneath a parabola, which is amazing because Archimedes did his work some 1800 years before Newton and Leibniz came up with calculus. We're going to use calculus to solve this problem. But it's amazing that, because he used this sort of weird proto-calculus to come up with the area, dividing this into little chunks. And we're basically going to do the same thing. So because I don't have a formula for this, by the way, you do have formulas for like circles. You know the area formula for a circle, right? It's easy enough, pi r squared. This we don't have there is a formula, but we're not going to talk about it yet. But because we don't have a formula, we're just going to do the best we can. And the best we can is I'm going to divide this up into little chunks. And we're going to do this in a minute with the paper you have there, but I just want to show you sort of pictorially what this looks like. So we can't find the exact area. Well, we can using calculus. But let's do this. How about that? That's good enough, isn't it? I'll bet you could figure out the area of those green rectangles because you know that when you plug 2 into this, you get 5. So this green rectangle would be 5 high and 1 across. This one would be 8 high because when you plug 1 into this, you get y equals 8. So we could just go along and add up all of these areas. So this is going to be 5 times 1, which is 5. This is 8 times 1, which is 8. This one is 9 times 1, because it goes all the way up to the top. This one's also 9 times 1. This one's 8, and this one's 5. So we could add all that up. Now, we would be overshooting, wouldn't we? I mean, that's too big. There's too much area there, but it still is an approximation. So that's one thing that we could do, is let's just sort of overshoot, and there you go. We could also undershoot, couldn't we? I mean, that's another way, like put all the rectangles underneath the curve. So that's another thing you could do. Excuse me. So overshooting it or undershooting it. We could do other things with this to sort of standardize the way we do this. In fact, this is called a right sum. So this, as we think about how we might approximate the area. And this, by the way, is not what Archimedes did. Archimedes actually used triangles, not rectangles. And it's nuts to see exactly how he did it, but if you persevere, you come up with the area formula. Here we're going to persevere, but we're going to find the area formula much easier than Archimedes because we have calculus to work with. But anyway, this one, here we could say this one probably is going to be a better approximation of that blue area than either of these. Because this one overshoots, this one undershoots, but this one kind of goes a little bit of each. You've got some overshooting the area, these areas, and these are undershooting. By the way, this is called a right sum because you'll notice that each of the rectangles is touching the curve at its right corner, upper right corner. So that's why it's called a right sum. Upper right corner touches the curve. We're going to actually do this with some of the curves that I gave you. I just didn't want you to have to draw it all and try to figure it all out. Let's do the next one. The right sum is one way of doing this. Another way of doing it is a left sum. Same idea. You're touching on the left side. We'll do this in just a minute so that you'll have a record of what a left sum and a right sum is. But just to see the picture, there it is. Now you might say, how is calculus involved in this? We're just drawing a bunch of rectangles and using geometry and making an approximation. Well, here's where the calculus comes in. We'll get the calculus maybe tomorrow, but I'll give you a preview. So you know what calculus is involved with. Calculus is involved with the limits, basically. Infinity is where calculus comes in. So here's what's going to happen is we have our sum, and we say, okay, that's good, but I could make it better by making the rectangle skinnier. So you would probably assume, and correctly assume, that if you divided up your curve using these rectangles that are skinnier, you are going to get closer to the truth than this. Than this. There it is. So this is going to be better, but of course you could say, well, why don't I just divide it up even more and even more than that? So eventually we'll have a limit, and it'll be the limit as the number of rectangles goes to infinity. You've got to get infinity here somewhere, right? So that's the way this is going to shake out. But for today, we just want to practice left sums, right sums, to understand where that's all coming from. And maybe even we'll do a midpoint just for fun. Okay, so let me see if I can find let me just see if I can find my version of this. Just discard all that. It's here. Just take a sec. But essentially what we're going to do is we're going to draw some left and right sums on this is the one that does not have the kidney-shaped pool. We'll get to the kidney-shaped pool in a minute. Okay, just a sec. Import, just have to find my file. Let's see, what did I call it? I should probably figure out what I named this thing so that I know what to look for. Classes. I've started naming my folders. Okay, it's sums activity. Like the folder for calculus is the number 1 and then calculus, so that it always goes to the top whenever I sort by. And then the calculus 2 is 2, because it's my second class, and so on. I should do the same with my files. Just name everything with a 0 at the beginning. It'll show up at the top. This won't let me sort by, here it is, finally found it. There it is, beautiful, isn't it? So let's just stick that there, and it's gonna be done, isn't it? Why? Why is it gonna be done? I don't know. What if I change this? Let's see. What if I do this? What if I just give up on this? Let's copy. I don't know if I can copy. Maybe I'll just go back to PowerPoint. Because PowerPoint isn't doing me dirty. So let's do it this way. Here we go. And then insert, insert picture. Why is it so hard to do this? There's my photos. I don't want my photos. Okay, I'm just going to go back. I'll suffer. We will all suffer together, though. It's like I need to get it at just the right magnification to make it happen. So weird. It's so strange. Why does it do that? Okay. Oh, okay. We got it. No, I'm not going to move it.
It's abstract art.
It is. It really is. I mean, I think of these artists. They do these sorts of things, and I could sell this. Okay. So you have on your sheet, you have 8 of these. 8 of them. And the reason why you have 8 of them is so that you can have sort of, did it mess up? Here, let me see. What if I cut, let's see, cut that, and then I paste it. It's still going to be done. What if I convert it to ink? Convert to ink. Still done. Why? Why does it do this to me? Okay, it's done now. Okay. Well, we're going to hope for the best now. Let me just copy this. Okay, mine looks different than yours. It's okay. Okay, so anyway, that way you can have several of these that you can keep track of. So what I'm going to do is I'm just going to label these. So this is going to be left sum. And the left sum where n equals 2, just to illustrate what's going on here. So if I have a left sum with 2 rectangles, then I need to make 2 rectangles. One of them is going to go from 0 to 3. And remember, it's going to touch at the left endpoint. So this is a kind of a dumb rectangle, because if you zoom in really close, which I don't want to do now because it's going to mess up my thing on the screen, that will be the curve. This curve actually goes all the way down and hits at the 0. So it's touching at the 0 there. That's boring. But then the other one goes up and across. There it is. So that's the left sum where n equals 2. We can actually compute, or at least approximate, this area. I'll show you how I do this. The area of this is going to be 0. Area equals 0. This has an area equal to approximately 3, because the bottom is 3. Oh, it's going to be dumb. I'll go in a bit further. Okay, 3 times, I'm going to go with 4.25. I mean, I'm just guessing at this point because I don't know exactly what that function is, but this will be close enough for your notes, because I just want you to have a record of what these look like. So 3 times 4.25 is 12.75. And so the total, this is the left sum, total area. I just don't understand why it does that. You know, maybe I just need to get another program that isn't going to be dumb. Just a minute. I'm sick of this. Here's what I'm going to do. Sorry. What is that? Undo. It's going to take a sec.
Are you using Visual Workspace?
What is that?
It's like an online whiteboard.
I don't want to use it.
Well,
Okay, there we go. Okay, so let's see. Here's what I'll do. Cancel that. Hold on a sec. There, I got it figured out. There, now I've got a copy of that. Now I go back here to PowerPoint, and here, okay, whatever. Yeah, here's my photos. That's what I want. Add, and then I'm going to crop this down. Just a sec. Crop. I know, it's like dealing with an old person. I used to think, I used to feel the way you're feeling whenever I dealt with my mother, who technology woes. Okay, that's better. Okay, and now I can just copy this. Check it out. Copy. Paste. Okay, so I will find a better program. I want it to be local, that's the thing. I don't want it to be online. I don't trust the interwebs. Okay, there it is. I don't like PowerPoint doesn't work as well as Notability, but if Notability can't show up on there, so I'm stuck with PowerPoint for now. Okay, so we've got, let's see, this is left sum n equals 2. We just redraw, whatever, very nice, beautiful. This one's a degenerate rectangle, area equals 0. This area equals 12.75. We already went over this. So the total area is 12.75. That's 0 plus 12.75. So we're good with that? Okay, so your job is to, on the next one over, we're going to do, whoops, why did it do that? Who cares? Let's try again. For the next one, you're going to do a left sum. So left sum, where n equals 3. Go ahead and see if you can come up with your approximation for left sum n equals 3. And then, of course, the next one you can probably guess is going to be a left sum where n equals 6. I know, I'm skipping 4 and 5 because I don't want to have to deal with them. So go ahead and draw as best you can a left sum where n equals 3. And then another one, left sum equals 6. And we're going to do the approximation, the area approximation of this thing. All right, let's try the n equals 3. So I don't know how to make you do it unless I brought this to you, but it's being problematic here. So why don't I just go ahead and draw on this? So you're dividing this up like this. So those are kind of the bottom corners of my rectangle. And as I mentioned, left sum, since you'll have to trust me that this function actually has a function value of 0. When x equals 0, it's going all the way down. That's just the way it is. Then probably up here somewhere, let's see, go up here. Does that look about right? And then this one will go up to about there. So these are going to be, I mean, since I don't know what the actual function is, these are definitely going to be approximations, but the purpose of this is so that you can actually see what these look like. So that you can see, this is what left sum looks like and what a right sum looks like. So let's get some guesses in terms of the approximations. Let me find my pick-me again. Here we go. So Ethan, okay, we already know this is area 0. What about the second rectangle, the one that's between 2 and 4? How tall did you think that was?
About 3.75.
Okay, so I'm going to do 2 times 3.75 for that one, which is going to be 7.5. Very nice. So let's keep a running tally here. 0 plus 7.5. Now we just need the last one. This is also going to be 2 across. So last one, Zach, how tall did you think that was?
It's like 4.75.
Yeah, I might as well keep it simple since we don't know what the actual function is. I'm sure I could dig it out of my files, but it's irrelevant. It's fine. We just use whatever. So that's going to be what, 9.5? And so this is my left sum when n equals 3, which is going to be 17 square units. Now, of course, you know that that's going to be an underestimate because you can actually see there's quite a bit of area here that we're leaving out of this area. You'd say, well, can't we just add up the squares? Well, yeah, but you have to deal with the fact that some of these squares aren't full squares. So this is just one way to deal with it. And interestingly, it doesn't matter if you have a limit. If we made these rectangles smaller and smaller and smaller, you would get the truth. You would get the right answer eventually. Well, using a limit. Okay, let's try this with n equals 6. Here again, we've got to deal with the rectangles. The first rectangle, of course, is going to just go be super flat. And that one, ooh, that one just goes up to 3, doesn't it? I'm going to go with 3 for that. And this one, oh, this one is similar to the one that we had just a minute ago, 3.75. Wait, we've already done all of these, haven't we?
No, just because we've gone to 1 strip to 3, so it's gonna come out to the same point again.
Yeah, oh, there's one that we are going to get to that we haven't done. So this one, so I'm just going to use the numbers that you guys gave me earlier because that one goes to the same point, and this one goes to the same point. This one is the new one. So that's the only one that we'll have to make a guess for. So how tall do we think that is? So Allison, how tall do you want that last rectangle to be? Okay, 5, I'm glad you chose that. I would have guessed a little bit smaller than that, but I like 5.25, just because it'll be a lot easier to compute things. But to be honest, I would think it was more like 5.1, 5.15, don't you think? It's not quite 5 1/4, but who cares? Because we don't know what this function is. This is just for illustration, and so the total area for this whole thing, this is an approximation once again. Let me add these up in my head real quick. That's going to be 10 plus 8 plus 3, which is 21 square units. So you can see we're getting closer and closer to the truth. Of course, I don't want to have to do this again with n equals, say, 20 or 30, but that is what we'll eventually do, at least with a limit. For today, this is as complicated as things get, but we need to have some examples. So I would suggest if you've done 3 of these with n equals 2, n equals 3, n equals 6, let's just go down below and do the same with right and just leave the last 2 blank for now. We're going to do right endpoints, so right sums for the next 3. So we're going to do a right sum, just to contrast, sum where n equals 2, do a right sum where n equals 3, and then a right sum where n equals 6. Just to contrast these, this won't take too long, but just do your best, sketch something in there. Oh, let me do the n equals 2 just in case you're like, what do we do? Okay, so here are sort of the lines that we're going to draw, but notice that this rectangle between 0 and 3 will touch its upper right corner instead of the upper left corner. So the right sum, you're touching the upper right corner, left sum, it's the upper left corner. So it's going to look something like this. So that first one, we've established, at least that's our guess, is that that middle point there is 4.25. I don't think we have a guess for the rightmost point, the f of 6. So I guess we can just take whatever you want. So Thomas, how high do you want that second rectangle to be? All right, I like that. It's probably not quite 5.5, but, you know, whatever. 5.5, I like it. So that's going to be 16.5? 16.5. So my area here is 12.75 plus 16.5. That's what, 29.25. But once again, you know that this is going to be an overestimate. This is too big, isn't it? You're overestimating by quite a bit over here. It's not quite as bad as the underestimate was, because the underestimate ignored a whole bunch of area, but it still is an overestimate of the actual area. So let's do the same thing with the right sum when n equals 3. You've already drawn it, I'm sure, but just in case, let me draw it here. Okay, so this is going to be 3.75 times 2, which is 7.5. This is going to be 4.75 times 2. It's really familiar, isn't it? 9.5. And then this is going to be 5.5 times 2, which is 11. So we have 7.5 plus 9.5 plus 11, and all of that together is 28. getting closer to the truth. So what do we have before? 29.25, now it's 28. Still, this is an overestimate. You can actually see where it's overshooting the actual truth. One more, right sum n equals 6, and then we'll get to some more, well, it's not a lot of formal stuff that we're going to be doing. Well, I guess we could get started with the sort of what the picture looks like. And so this will be 3. I'm just going to write it at the top here, because the reason is just 1 across. So it's 3 times 1 plus 3.75 times 1, which is 3.75. Let's see, that's going to be, was it 4.25 that we used before? 4.75, 5.25, and 5.5. Wow, so much to add up, but I think what I could do, since I've added this stuff up already, it's just going to equal 21 plus 5.5, so it's 26.5. That's my sum. No, I didn't do it right?
No, I was just noticing how the numbers were the same from the lump sum that shifted over by.
Yeah, so it's like you've taken these rectangles and you like shove them over, and then you have the extra rectangle there. Yeah, so left sums and right sums, there's a relationship. And I should say that it's not always the case that the right sums are an overestimate and the left sums are an underestimate. Just so you know, it can go either way. It just depends on the way the curve is. In fact, we'll see at least one. Well, actually, the first one on this page, you'll see is it's going to be the other way, the opposite way. Okay, so next, what are we doing here? How about let's see. You have 2 more of these that you could fill in. So why don't I do this? We'll do this: midpoints with n equals 3. So let me explain midpoint. So what's the midpoint if we're doing that? What it means is that, so n equals 3 just means you're going to divide this into 3 rectangles down here. The midpoint means that the height of the rectangle will match the function at the middle of the rectangle. So instead of going on the left or the right, maybe if we do the middle, that would be better. And actually, it's quite a bit better. But let's just do that. We'll do this, goes up to there. And then the next one goes up to here. So just so you have a picture of what this looks like. And this one goes up to here. And you can imagine why the midpoint would be a useful way of thinking of doing this, because you kind of cancel out the area that you've overshot and the area that you've undershot kind of balances out. I mean, not perfectly, of course, but I mean, it's going to be better than just overshooting the whole thing or undershooting the whole thing. So we might as well, let's do this one. This one's going to be 2 times 3. This one will be 2 times 4.25 and 2 times 5.25. Once again, I think that 5.25 should be a little bit lower, but just for simplicity's sake, we'll do it this way. So this area, I guess all of these should be more approximate or approximately equal to the area of the rectangles. Of course, we're doing the actual area, but we're approximating the gray area. So the area is approximately 6 plus 2 times 4.25 is 9.5? No, 8.5. 8.5. And then this will be 10.5? 10.5. So let's see, 8.5 and 10.5 is 19, 25. So midpoint turns out is oftentimes a better measure. Okay, let's just take a brief look at the ones I have here on this page. I'm going to do my best to put it on the screen here, but you can just do these. And so what I would like to do, I was thinking I would use n equals 10. Here, let's do it this way. I want to do 3 of these because I want to save C for later. C is special, so you want to save that, and we'll save the others. But let's do letter A, and do letter A with n equals 10. No. N equals, just such a large number, so many calculations. No, let's skip down to E. Let's skip down to E for now, and then we'll go back if we have time. Because A and B are very similar to what we just did. Oh, and by the way, you might wonder, you hang on to these papers because we're going to use them in the future. At the bottom of this one that we just did, the gray one, the speed and time, we'll be dealing with that. That's coming up. But save that for later. But I love E, so let's see if I can make E work here. Just a sec. Let's close that. Yeah. But anyway, you can, oh yeah, basically I want you to use, let's do left endpoints, make rectangles, and compute an approximate area for that kidney-shaped swimming pool. That's the idea there. So I will try my best. Camera not available. I need to somehow make the camera available. Why don't I just take a picture? There we go. Beautiful. Now I can go back to PowerPoint. Yeah. That one. That's so nice. Oh, alright.
You said left, right?
Yeah, use left. Undo. Good enough. There, it's kind of ugly, but it will work. So you notice that this pool, it's a pretty big pool now that I think of it. If these are feet, yeah, this is a really large, maybe it's like a pond. That's maybe a better thing, but maybe it's a pond. So if you think of this as a left end point, then each of these sides. So let me get you. Let's do this. Let's start with this one here. There. I know I'm starting in the middle, but I just want to show you sort of the way to think about this. Is in that middle one there, the rectangle is going to look something like this. And the area of that rectangle is 8 times 26. So you see how I've done that? I've made my rectangle. It's a little bit askew there. But I've got my rectangle. 8 times 26 is the area of that rectangle. You could do the rest of them, couldn't you? The only problem, child, is the first one, right? The one on the furthest to the left. So let's do the furthest to the left one. The left end point is 0, so there is my rectangle. And the area of that is 0 times 8. Now you might feel bad about that rectangle, that you're underestimating the area, but notice on the other side of the pond, I have this rectangle that is way overestimating that chunk, and that's going to be area is 24 times 8. Well, hopefully you did something, or at least got started with something like this. This is 20 times 8. This one is going to be 32 times 8. This will be 33 times 8, if you'll forgive me for not drawing. 35 times 8, 36 times 8, 31 times 8, and we've got the 24 times 8. But the long and the short of it is that if you wanted to know approximately the area of this kidney-shaped pond, you could measure the distance across at various intervals, and then just add up the areas. 20 times 8, well, this 0, then 20, then this. Add them up, and you'll get approximately the area. It's not going to be perfect, but sometimes you're overshooting, sometimes you're undershooting, and hopefully it'll balance things out. All right, let's just take a quick peek at the homework. Bring these papers, because we're going to use them. So don't lose them, because you're going to want to use them. Let me just find that's not it. Hold on a second, I need to find my homework stuff. Let's see this thing, let's go back to this, just to show you what this is gonna look like. Let's see, related rates, we don't want that. It's the next thing. We're starting areas, integration. Where are the areas? Here we are. Approximating areas, part 1 is due tomorrow. So let's just take a peek real quick and make sure that you understand, because the questions are going to look a little bit different than what we've done, but it's the same idea. So the deal here is that they give you a function and they say approximate the area using eight rectangles. And so what that is referring to is you can sketch this graph between 0 and 2, and then divide that up. It'll be 0.25 for each one. So they're going to be really skinny rectangles. We've had fatter rectangles, but you're going to approximate the area underneath that curve. 8 is a little bit much. I thought that let me see if I do 10, 4 there. I suppose that if you get can you get new versions yourselves?
Yeah, but there's only one way now.
Only 3? I can change the settings on that one. Yeah, I guess if you click enough times, maybe you'll get something with 4 rectangles. Right in point with 6 subdivisions. So this is a similar deal. You have x cubed, and so the x cubed is just the function. Where is it? There it is. So it's the function that you're actually, so you would be like, this is y equals x cubed. It's not, but you could pretend. And then, where is it? It says going from x equals 2 to x equals 5 using 6 subdivisions. So you'd be like from 2 to 5. So I need 6 subdivisions here. There we go. And right endpoints would be something like this. And then the only difference between what we did is instead of guessing as to how tall the curve is at each of these points, since you have the function, you can actually say, when x equals 2.5, for example, the function value is equal to 2.5 cubed. So you can actually compute that on your calculator. So do your best with those. We'll pick up the pieces tomorrow, I'm sure. In the early study session, right? We always have the early birds come to do their homework. I love that. Yeah, hopefully, as long as the floods subside. Okay, I'm going to stop.